Hello. And so far we've discussed the receiver operating characteristic curve, which is a curve of the false positive rate of a classifier against its true positive rate. And it gives a pretty good summary of the overall behavior of a given classifier across different values of threshold. So for each value of the threshold, we calculate its corresponding true positive rate and false positive rate, and then we get a plot like this. It gives you a good summary in the sense that you can analyze what can be the expected sensitivity along the y-axis. So that is sensitivity or true positive rate. It is also called recall, so all of these things are the same, and you can get an idea of what would the recall be at a given false positive rate. So let's say if we fix the false positive rate to, let's say, 0.1% or zero point 0.1 or 10%, then you can calculate what is the expected sensitivity or recall. And we have discussed that this ROC curve, is going to be a monotonically non-decreasing curve because of how false positive rate and true positive rate change as we increase the threshold from a very low value to a very high value. And we've also discussed the ROC curve of a random classifier. It's going to be a curve like this one or close to this one. And as a consequence, the area under the ROC curve for a random classifier or classifier that is behaving randomly is going to be 0.5 because it's half of this square, right? And for an ideal classifier, we've discussed that the ROC curve for an ideal classifier is going to go up. So it's going to produce a true positive rate of 100% and a false positive rate of 0%. So it doesn't generate any false positives and classifies all of the positives correctly. And this is going to be the curve, and the area under that curve is going to be 1.0. So we can use area under the ROC curve as a quality metric. However, ROC curves also make certain assumptions, especially in terms of data imbalance. So they, just like accuracy, they are also impacted by data imbalance. They have some really good properties as well that we've discussed, that they can be averaged, and you can get a convex hull of different classifiers. So that gives you an idea of what is the expected accuracy or what is the expected performance of a set of classifiers if you average their outcomes in an optimal manner. Okay, so these are some of the properties, but due to this imbalance issue, just like accuracy, they are not recommended for use if the imbalance is too high. Let's say if you've got 100 positive examples and you've got 1,000 negative examples, then ROC curves are probably not a good idea. If the imbalance is like 100 and let's say 150, it's not that severely imbalanced. So if you got 100 positive examples and 150 negative examples, you can probably still go ahead and use ROC curves and analyze and use them as a performance metric for your classification problem. But if your test set is severely imbalanced like this one, then we have a problem. Class imbalance is a big issue in when developing machine learning models, and the reason for that, in some conditions, for example, cancer, are pretty rare in the general population, right? So detecting cancer out of all of the examples that are given as test examples to a classifier is going to be really hard. Similarly, the coronavirus, for example, if you want to make a machine learning model that takes in some symptoms and predicts whether a person has coronavirus or not, the vast majority of people don't have the virus, or they're not showing symptoms of it. And that classifier, we need it to perform really well on in detecting those few positive examples that we expect to see in the population. So class imbalance is a big problem. And analyzing the performance of over a test set or over a problem where the number of positive examples is much smaller than the number of negative examples, that creates certain issues that are not resolved using ROC curves. As a consequence, we move to the next type of performance metric, and it's also a curve. It's called the precision recall curve. Okay, so the ROC curve, as we just discussed, is a plot of the false positive rate of the classifier against its true positive rate. So it's a plot of, you can think of FPR as 1 minus the specificity, and on the y-axis is sensitivity, right? So that is what the ROC curve is. Okay. In contrast, the PR curve or the precision recall curve plots the recall which is equal to the sensitivity, which is equal to the true positive rate of the classifier at a given value of the threshold for that classifier against the precision. So the precision is, if you recall, the precision of a classifier at a given value of its threshold is the number of true positives that it has detected out of all of the positives that it has predicted. So this is P prime. P prime is the number of positives that have been generated for by a classifier. So let's say if you've got a classifier that predicts 1000 examples as positive, but only out of these 1000, only 100 are actually true positives, then your precision is going to be 10%. So it's a pretty low precision value. And precision is a very good metric to use when you are dealing with imbalanced data sets, especially in cases where the number of positive examples is much smaller than an overall than the number of negative examples in your test set. So precision gives you an idea of how precise your predictor is, or what is its ability to spot the right positive examples out of all the negative examples. So if your problem is to find the needle in the haystack, then because the haystack is pretty big and the needle is going to be small, if you're trying to detect a minority class out of a majority of negative examples, you should use precision as your performance metric. So if you take a curve and you plot the precision of a classifier against its threshold. So if you take the threshold value and you change it over time from minus infinity to plus infinity, and you plot the precision on the y-axis, much like what we had done when we were dealing with ROC curves, you would get a curve, right? So at a certain value of this threshold, you would get a certain value of the precision. And that value can change as we go along, as we change the threshold. But unlike sensitivity and false positive rate or recall and false positive rate, precision of a classifier is not monotonically increasing or a monotonically non-decreasing function. It can go up and down depending upon how many positive examples are predicted at a certain value of the threshold and how many examples out of those predicted positive examples are actually true positives. So it's not a very well-behaved curve, the precision versus threshold curve. As a consequence, your precision versus sensitivity curve, which is the PR curve or the precision recall curve, can also bounce around and it can go up and down as you can see for in this example. So what you see on your screen is the ROC curve for two classifiers. We call them algorithm 1 and algorithm 2. And you can also see the ROC, the precision recall curve. So this is the ROC and this is the PR curve for these classifiers. So what we have done in generating these is for a given algorithm, we have calculated their false positive rate at a given value of the threshold and plotted it against the true positive rate to get the ROC curve. Whereas for the same classifier, we have calculated the sensitivity of that classifier against its precision at a given threshold, and that gives rise to the PR curve. Now, since precision is not a well-behaved function of, by well-behaved, I mean it's not monotonically increasing or monotonically non-increasing, it can go up and down as we change the threshold. Therefore, the PR curve, unlike the ROC curve, which is a monotonically non-decreasing function, can go up and down as you can see in this plot on the right. Okay, if you want to relate the concept of precision recall curves, you can say that since this is sensitivity or this is recall, so true positive rate is the same thing as recall or sensitivity. So the y-axis of an ROC curve is the same as the x-axis of the PR curve. So this axis is exactly the same. This is the sensitivity. However, the y-axis of the of the precision recall curve is different from the x-axis of the ROC curve. The x-axis of the ROC curve plots the false positive rate, which is 1 minus the specificity of the classifier at different values of the threshold, whereas for the PR curve, we have something completely different, which is the precision. So this is going to be a very different, conceptually a very different curve for these two, for in comparison to the ROC curve, right? And just like in the ROC curve, we can measure the area under the curve for a given classifier, and that is going to give you a performance metric. And ideally, what we want from an ideal classifier is that we want 100% recall and 100% precision. So this point over here is where we want the classifier to be. This is the value of an ideal classifier. We want all of the positive examples to be predicted, and we want only the positive examples to be predicted as positives, nothing else. So the precision is going to be 100%, and the recall or the sensitivity is going to be 100%. And unlike an ROC curve, where we want that the false positive rate should be zero and the true positive rate should be 100%. So this is the ideal uh, classifier, and this is the ideal classifier in the same classifier in the PR space. So if you have an ideal classifier in the ROC space or in the ROC curve, the corresponding point for that classifier is going to be this one in the PR curve. Okay, and you can, as I said earlier, you can measure the area under the curve. If for an ideal ROC curve, the area under the classifier is going to be 100% or is equal to 1. Whereas in the PR curve, it's again going to be 1, but for very different reasons. For that, the precision is going to be 100% with the sensitivity equal to 1. Okay? So I hope you are able to understand that this point gets mapped to this point in the ideal case. However, we know that for a random classifier, we get an ROC curve that looks like a line smack in the middle, and which divides this square into two parts, right? For the precision recall curve, for a random classifier, this is not going to be the case. Do not expect that the area under the precision recall curve of a random classifier is going to be equal to zero point 0.5. I welcome you to think about that and understand why that would be the case. As a matter of fact, the area of under the PR curve for a random classifier depends upon how many negative examples there are. So it can change depending upon how many negative examples there are in the test set, whereas for any test set with any number of negative examples, the area under the ROC curve for a random classifier is always going to be close to 0.5. Okay, so that's another difference between the two. Okay, so if you look at these two curves, which I really messed up on your screen, we can say that algorithm one, if you look at it, the data shown by this solid line over here, has a much lower true positive rate at a given false positive rate. So if you measure the performance of our classifier at, let's say, a false positive rate of this much, then for algorithm one, the TPR is this much, whereas the true positive rate for algorithm two is this much. So we can say that algorithm two at this operating point of false positive rate of 0.1 has a much higher true positive rate. So algorithm two is actually better than algorithm one in this case. If we come to the corresponding PR curve on the right-hand side of your screens, we can see that we have the recall plotted over here on the x-axis and the precision plotted on the y-axis. If you look at a certain value of recall, let's say if we compare at about 60% of recall, a sensitivity of about 60%, which corresponds to this operating point, right, over here along the y-axis of the ROC curve, we can see that the precision of algorithm 1 is much lower. It's close to about 10% for algorithm 1, the solid line. And in comparison, we can see that the algorithm 2, its precision is actually much higher. It's close to 30%. Okay, so this is about, let's say, 10%. And we can say that at this operating condition or at these operating point where you want 60% recall, the algorithm 2 is actually better than algorithm 1. So the same conclusion follows whether you analyze it in the PR space or in the ROC space. Okay, so if a classifier, and there's a proof for that, which we will not cover in this part of the module, there's a proof that if a curve dominates if an algorithm dominates another algorithm in the ROC space, it's going to dominate the same algorithm in the PR space. So if an algorithm is showing up as better in the precision in the ROC space, it's going to still be better in the PR space and vice versa. Both of that's the correspondence between the two. However, it depends upon the number of examples. So let's say if the examples are balanced. So if you've got a balanced test set, let's say if you got a number of positives to negative ratio, so positive to negative ratio of 1 to 1. So in this case, the examples are balanced. Both of your curves are going to look, they are going to be pretty much the same. So this is what happens when this is the ROC curve on this axis. This is the corresponding PR curve. And as you can see, if you have got two algorithms, let's say we've got a solid line algorithm and we've got a dotted line algorithm. Let's say we're comparing the performance of these two algorithms. We can see that the dotted line algorithm on your screens offers much better sensitivity. On the x-axis of this is going to be false positive rate, and on the y-axis is going to be the true positive rate or the sensitivity, whereas in this case, it's going to be TPR is going to be on the x-axis, and on the y-axis is going to be precision, right? Because it's the PR curve. And as we can see that when the TPR, the true positive rate, if you calculate the true positive rate of both of these algorithms at a very low false positive rate, let's say we do it at this point, we can see that the dotted line algorithm, or it's a solid line algorithm actually, produces a precision, true positive rate of around 0.35, and at that particular value, the true positive rate of your dotted classifier is going to be much higher. So it's zero point 0.5, around zero point 0.5, and this is around 0.35. So we can say that the dotted line algorithm is actually better at this operating point where the false positive rate is low. And and if you look in the at the classifiers in the precision recall space, then we can see that at a recall of zero point 0.5. So if you take a look at this curve, we can see that the dotted line, the solid line algorithm gives us a precision of around 0.9, whereas the dotted line gives us a precision of around 0.95 probably. So the dotted line algorithm is better at this operating point in comparison to the other one, right? So they have pretty good correspondence. Similarly, you can calculate these at another value of the false positive rate, and you can analyze their performance there as well. So in this case, the solid line algorithm is actually better than the dotted line algorithm. So both of these curves, and if you compare it in the corresponding space, you will also be able to see the same effect. However, really things start to get interesting when we have data imbalance, right? So let's say if the number of positives, the ratio of the positive to negative examples is 1 to 10. So for every 10 examples, every 10 negative examples, there is a single positive example. Then we have got class imbalance. Now, the ROC curve is not impacted by this class imbalance. Therefore, the curve, as long as the classifier is the same, and the only thing that changes is the ratio of the positive to negative examples, you are going to end up with the same ROC curve as you had for the class ratio when it was 1 to 1. And that is because ROC curves, because they are based on false positive rates and true positive rates, they are not impacted by the class imbalance ratio. Okay. On the other hand, the PR curve is going to change significantly. So this is the PR curve, and you can see that this curve over here is significantly different for a different class ratio in comparison to what we had when the class ratio was balanced. And this is more informative in this case for this particular comparison in contrast to the ROC curve. Okay, so in case of data imbalance, you need to use you can use precision recall curves, because in such cases where the number of negative examples can be much larger in comparison to positive examples, we actually want the classifier to pick out those positive examples from the sea of negative examples, and and this is what it's doing. And we can see that over here, the dotted curve that you see. So let's call that algorithm 2, this one, or we can call it the dotted algorithm. and we've got a solid curve coming from a solid algorithm, just give them names, we can see that although at a certain value of the true positive rate, so on this axis is true positive rate, and on the y-axis is precision, and over here you've got a true positive rate on the y-axis, and you've got false positive rate on the x-axis. Okay, so if you think about it a bit, false positive at the true positive rate at very low values of false positive rate actually indicates or is related to precision much more than high false the true positive rate at high values of false positive rates. Okay, so this part of the curve of the ROC curve impacts the precision recall curve much more than, let's say, this region. So if you have a data imbalance problem, and you are given the ROC curve of two classifiers, and one of the classifiers, let's say the dotted classifier in this case, is better shows better performance at low false positive rates in comparison to another classifier, say the solid line classifier, then I can safely say that the precision in the precision recall space, the dotted classifier is going to dominate the the solid classifier as it is being shown over here uh, significantly. So, if you have a high data imbalance, you should pay attention to this particular region of the ROC curve, which corresponds to low false positive rate. So, ideal classifiers should have a very high true positive rate at very low false positive rates. Okay, and that's what we've discussed. So this point over here gets mapped onto this point in the PR curve space. So it's important to understand this correspondence between the two and relate it to how classifiers, especially in data imbalance cases, we should analyze their performance at low false positive rates, or in other words, we should analyze their performance at high precision rates. Okay, so I want you to understand, think about the correspondence between these two and try to understand the difference between them. If you compare as I've told you, we can use the AUC PR as a performance metric, right? So that is the area under the curve, and that can be obtained by integrating numerically the area under each of these curves. And if you calculate the area under the precision recall curve for the two classifiers, when we have data, we have no data imbalance, or the test examples are roughly balanced. You can calculate the areas under these two curves, and they are going to be pretty much, or they are going to be pretty much close to each other. But for this case, when you have severe data imbalance, your AUCPR for the dotted line is going to be much higher in comparison to the solid line. And that shows that if you want to use, uh, uh, this gives you an idea of what classifier to use when you have higher imbalance, and it's the dotted classifier. Okay. So I hope this summary makes good sense to you, and you now have a better understanding of precision recall curves. Just to summarize, precision recall curves plot the precision along the y-axis and the sensitivity along the x-axis, in contrast to ROC curves, which plot the true positive rate on the y-axis and the false positive rate on the x-axis. It's one easy way of remembering or helping you remember how to interpret these curves is to remember what an ideal classifier looks like in both of these spaces. So an ideal classifier in the ROC space would be here, where the uh, true positive rate or the sensitivity is 100% and the false positive rate is 0. Whereas in the precision recall space, we want a classifier that has a 100% true positive rate and a 100% precision. Okay, so that way you can remember which of the two classifiers is better. And now I'm going to ask you a series of questions that is going to help you understand this thing better. So let's say if you've got, I'm going to plot a series of examples of ROC curves and PR curves in the next video, and we are going to and that is going to help you understand these concepts and relate them to each other in a better way. Thank you.